Okay, let's derive some identities, just like I promised we would. So to start, we're going to do the compound angle identity. Compound angle identity, or formula, as you might hear it referred to. How do we derive this? Well, what we're going to do is we're going to start with cos of a plus b equals cos of a, cos of b minus sine a, sine b. So that's the first one we're going to do. Now I'm going to draw a plane here, like that. And I'm going to say, all right, where is the point cos of a plus b and sine of a plus b? Or maybe we should start with just angle A, right? If you think of angle A, let's just say this is angle A, just because this coordinate would be cos of A, sine of A, right? Because cos A represents the x value and sine A represents the y value. Now, if I said, okay, well, what about angle B? Well, angle B could be this angle in between. So that means that this whole thing to get to here is A plus B, right? To get all the way there is A plus B. So the coordinate here would be cos A plus B sine A plus B. Just like that, okay? What we could also do is I could go down here to negative B, right? And I could call this point R. And point R is at the coordinate cos negative B sine negative B, which we can simplify to be cos B negative sine B. And the reason you can simplify it like that is because cos of a negative number is equal to cos of a positive, right? Because whether you're going like up or down, the cos value is the same. They're both going to the right. But the sign changes whether you're going up or down, right? Because a positive sine value, you get a positive number like this. But if you take sine of a negative number, you're going down. You get sine of that negative number, you get a negative height, right? You're going down. So you simplify that to that. I want to make clear a couple things that are happening here. You have one triangle where this is coming down like that. It's going out like this to, I'll call this point L. That's just when the line is going straight out, right? And then you can connect those two together like that. So you have this big red triangle. And I'm actually going to label some of these points. I'll call this O for the origin, and I'll call this up here Q, right? So you could have triangle OQL. I'll draw it on the side here just to show so it's not so messy. We know angle O is A plus B. I know this length is 1. I know this length is 1 because those are just the radial arms, right? That's the radius, right? So those are both 1. And I also know another triangle here, right? We know this triangle that goes like this. Right, that's a triangle. And we can draw that one as well. Something like that, where these lengths are both 1, right? This here, what angle is this? Well, this part was A, and this part was negative B, but its actual angle is B, right? The negative just indicates direction. So the whole angle is A plus B, right? So this angle here is also A plus B. And this is O. We don't have a name for this one. Let's call this little point here P. So that'll be P. And then this down here we called R, right? So from these points and all these lines, we made these triangles, right? And what can be said about these two triangles? Well, if you look, they both have the same angle, and they both have a length of 1 and 1, right? 1 and 1. So it looks like those triangles are similar triangles, or actually it goes further than that. They're congruent triangles because they're the same, right? You could say triangle LOQ is congruent to triangle POR. Okay? So these two triangles are the same. It's just oriented a little bit differently, right? In fact, what we would call that is SAS congruence. And if you remember the lesson on that from last year, side, angle, side. If you have the same side, angle, and side, angle, and side, that makes those two triangles congruent or the same, right? That's one way to tell. So if those two triangles are exactly the same, then wouldn't that mean that side QL is the same as side PR? I think it would, right? So you could come down here and we could say that QL is equal to PR. Now what is QL? How do we solve for QL? Well, QL is just, what is QL? It's this length here. How would you find that? Right? How would we find this length over here? Well, if you think about it, this triangle here, where you have a right angle triangle, QL is the hypotenuse of that right angle triangle, right? So if you could find this length and this length, you could find QL. Now how could you find those two lengths? Well, I know the coordinates of Q and L, so you just subtract the x values and the y values, find these lengths, and that'll give you the side QL, right? Pythagorean theorem. So let's go ahead and do that. So for QL, that's going to equal the square root of x1 minus x2 squared plus y1 minus y2 squared, right? If you plug in all those values, x1 is cos of A plus B, and x2 was just 1, so we're going to subtract 1. y1 and y2, we have sine of A plus B. y2 is 0, so minus 0. If you're confused where I'm getting the negative 1 and 0, I'm talking about point L, right? Point L is here. The coordinates there are 1, 0, right? Because it's just going to the right one and it's not going up or down. That is point 1, 0, right? And then point Q, we have these coordinates for that. So I'm just doing, subtraction of those x values here and the y values there. And again, that's going to give me this distance here. When I subtract the x's, it gives me the horizontal distance. And then when I subtract the y values, you get this distance here. That makes a right angle triangle. I'm using Pythagorean theorem to find QL. Okay, that's all I'm doing here. Now I can also find PR, right? Because they said PR and QL are equal. Well, PR, if you do the same process, you're going to get cos A minus cos B squared plus sine A plus sine B squared. How did I do that? Well, remember, PR is this here, right? Well, same idea, right? If you have a triangle here that goes out and then down, right, it's going to be a 90-degree triangle. It's a lot skinnier than this one is from the drawing, but it might not be, right? These are just general, angles A and B, right? So that could be any exaggeration of a right angle triangle. You subtract the x values and the y values. Well, what are the x values for P and R? Well, R, you have cos of B, and for P, you have cos of A, right? For the y values, you have negative sine B and sine of A. So when you subtract those, cos A minus cos B, and then sine A minus negative sine B, it becomes plus, right? That's how you get that. So because we said that QL is equal to PR, I can equate these last two expressions that I just came up with, right? I can equate these two things because they're equal. So we can go ahead and say cos of A plus B minus 1 squared plus sine A plus B minus 0 squared is equal to, I'm going to try to fit this in, cos A minus cos B squared plus, this is going to be sine A plus sine B, and that's also being squared. So you can kind of see I squished that in, but that's okay. So if you expand this all, you're going to get cos squared, and I canceled those square roots on both sides, right? These were both square rooted, but it's on both sides, so it cancels. Anyway, if you expand this, you get cos squared A plus B minus 2 cos A plus B plus 1 plus sine squared A plus B, like that. And that's going to equal cos squared A minus 2 cos A cos B plus cos squared B plus sine squared A plus 2 sine A sine B plus sine squared B. Okay? All right, so now what we can do is we can start to solve for this guy here, right? Because again, we're trying to show the proof that cos of A plus B is equal to, cos A cos B minus sine A sine B. So I want to isolate for this eventually. So I'm just going to move everything else to the right. So negative 2 cos A plus B is equal to, I have all this stuff. I'm also going to move these two things over to the other side, okay? And when you do that, you're going to start to see some things cancel out, right? Like I have cos of A squared here, and then I also have plus sine A squared over here. And if you add those two together, they become 1, right? Like from the Pythagorean identity, they add together to be 1. And then I have cos squared B and sine squared B. They also add together to be 1 from the Pythagorean identity. So 1 and 1, that's just 2. So really what I can do is I can just put the number 2 here, plus 2, and these will go away and those will go away. It's all there in the number 2. So all you have is minus 2 cos A cos B plus 2 sine A sine B plus 2. So now I have on the, wait a minute, on the left side I have cos squared A plus B and sine squared A plus B. Well, remember, cos squared of something plus sine squared of something, that's equal to 1. It's another Pythagorean identity. So those go away and you get 1. Bring the 1 to the other side, you subtract it. 2 minus 1, that's just 1. So really what I have is this is equal to negative 2 cos A cos B plus 2 sine A sine B plus 1. That's really all I have so far. And wait a minute, almost forgot, there's also a plus 1 in here. Bring that to the other side, right? It's going to cancel with the 1 here, so that 1's actually gone on the end, right? Forgot about that one. So now all you have is this. Divide both sides by negative 2, and you'll get cos A plus B equals cos A cos B minus sine A sine B. So it actually works out pretty nicely, right? So this proof is a little bit of work because you have to imagine A and B on an actual plane, right? So this is a bit of work. But after you get this one, solving for the rest of them isn't too bad, right? Because they can all be derived from this one. For example, if we know what this is, I could say, well, what's cos of A minus B, right? Well, you would say, okay, well, so it's cos A times cos, instead of B, I'm going to put negative B. So I'm just using this pattern, minus sine A sine negative B. Well, cos of a negative is the same as cos of a positive, so this is the same, cos A cos B. But then this over here, sine of a negative is equal to negative sine of that thing, right? So the negatives will cancel, and you'll get plus sine A sine B. So this is the second one, right? Cos of A minus B. See how fast that was? Okay, what about the sines, right? Because of course the cos is going to be easy, but what about sines? So let's try to figure out sine of A plus B. Well, sine of A plus B, that's going to equal, if you remember, cos of pi over 2 minus A plus B, right? Because remember, we say that sine of theta is equal to cos of pi over 2 minus theta. Remember that one? I think that's a co-function identity, right? We covered that in the last video. Using that, you can change sine to cos. So really what you have here is cos of this minus this. Or you could rewrite this and say this is cos pi over 2 minus A minus B, like this. Distributing that negative and then bracket the first two. Why would you do that? Well, because now you can split this up using the cos of A minus B, right? You could say this is cos pi over 2 minus A times cos of B plus sine of pi over 2 minus A times sine of B. What's going to happen here? Well, cos of pi over 2 minus A, remember from this, that's just equal to sine of A. So you get sine of A cos B plus this, if you use this rule here, or not that one, but the other one, the one that says cos of theta equals sine pi over 2 minus theta, that's going to equal cos of A sine B. So just writing that again, so that's your third one, right? Sine of A plus B is equal to all this. And then to find the last of the four, you say, okay, what about sine of a minus b? How do I find that? Well, just plug in negative b for this. So sine a cos negative b plus cos a sine negative b, and then simplify it, right? So what happens? Well, cos of negative b is the same as cos of b, so you can just write sine a cos b. But when you take sine of negative, it becomes negative, so negative cos a sine b. And there you have it. So that is how you derive those first four compound angle identities. Okay? Now, what about the tan, right? Because isn't there a tan of a plus b in here? There is, right? So tan of a plus b is equal to sine a plus b divided by cos a plus b. Well, these are defined now, right? Because sine of a plus b is sine a cos b plus cos a sine b. And then cos of a plus b is cos a cos b minus sine a sine b. That's the first one we found. Now what's going to happen here? Well, what we have to do to simplify this is we're going to divide everything by cos a cos b, and you're going to see why in a minute. If I divide all these four terms by cos a cos b, what do you have? You have sine a cos b divided by cos a cos b minus cos a sine b divided by cos a cos b divided by cos a cos b over cos a cos b minus sine a sine b over cos a cos b. So I divided each of those four terms by that. What happens? Cos b and cos b cancel. Cos a and cos a cancel. This whole thing cancels. And over here, what happens? Well, it doesn't look like anything cancels, right? So what are we left with? Well, sine a over cos a is tan a. Sine b over cos b is tan b. On the bottom, you get 1 minus sine a over cos a is tan a. Sine b over cos b is tan b. That's it, right? Tan of a plus b is equal to this, right? And then for the negative, right, because we got to do tan of a minus b now, tan of a minus b, that's equal to, I'm just going to plug in negative b, okay? So tan of a minus tan of negative b divided by 1 minus tan a tan negative b. How does that simplify? Tan, oh, there should be an n in here. That's tan of a. Well, when you take tan of a negative number, that negative comes out, right? Because there's a sign in there. So that becomes tan of a plus tan of b. Oh, sorry, made a mistake. This should be plus because that's plus. I don't know why I changed that to a minus, but that's a plus on the top, right? That's a plus. Don't forget about that. That's my mistake. Now here we have a plus, right? So the minus and the plus together, that becomes minus. So tan a minus tan b. There we go. That makes sense. And then on the bottom, 1 plus tan a tan b. So this is your answer for tan of a minus b. Tan a minus tan b over 1 plus tan a tan b. Okay. I think that's the first mistake I made, but I'm sure people in the comments will point out more. Okay. Now that was the compound angle. Now let's talk about the double angle identity, right? Double angle. This one's not as difficult to figure out, right? Because sine of 2 theta, that's actually equal to sine of theta plus theta, right? So we can rely on the compound angle identities to figure out the double angle identities. So if you remember sine of a plus b, that's equal to sine a cos b plus cos a sine b. But the difference here is a and b are the same. It's just theta and theta, right? So what you get is, well, these two terms are the same, so it's just 2 sine theta cos theta. And that's it, right? That's your double angle identity for sine. Now, for cosine, it's a little bit different, right? Because cos of 2 theta, you'd say that's equal to cos of theta plus theta, which is going to equal cos theta minus sine theta, and that equals cos squared theta minus sine squared theta. So that's one of them, right? That's one of your definitions for that. And if you decide to plug in the Pythagorean identity, right, and say that, well, remember, sine squared theta plus cos squared theta is equal to 1. If you isolate for one of these, you can plug it into this, right? Like if I were to isolate for cos theta here, or cos squared theta is equal to 1 minus sine squared theta. So plug that in here, right? If you do that, you're going to get 1 minus sine squared theta minus sine squared theta, which is equal to 1 minus 2 sine squared theta. That's the second definition for this, right? That's the second double angle identity for cos of 2 theta. But you could also isolate this for sine squared instead, right? You could say sine squared theta equals 1 minus cos squared theta, and then plug that in for sine squared, right? And if you did that, then you would get cos squared theta minus 1 plus cos squared theta becomes plus because it's minus minus, right? And that would become 2 cos squared theta minus 1, and that's the third definition for cos of 2 theta, right? So that's where those all come from. That's how you can find those. And then finally, we have tan of 2 theta, which is going to equal tan theta plus theta, which you could say is equal to tan theta plus tan theta divided by 1 minus tan theta, just like that. And that's going to simplify 2 tan theta divided by 1 minus tan squared theta. So the double angle identities are really just a special version of the compound angle identities, right? Where both of the angles are the same, and therefore you can just rewrite it as tan of 2 theta or sine of 2 theta or whatever instead of theta plus theta, right? A plus B. Because they're the same, you can write it like this, and then you just simplify the compound angle identity to be a double angle, right? And that's it. So that's the proof or the derivation for the compound angle identities and all the double angle identities.